Okay. Now let's have a look at insertions in the path integral. So far we have the statement that integral dx I to f e to the power I by h bar s I f of x is given by this is equal to this matrix element f I, right? So which can be calculated using matrix mechanics and so on. Now more general relation will be would be of this sort: dx I to f e to the power I by h bar s I f of x, and then there are some insertions, and correspondingly we would have on this other side f and some insertions I. That is a natural guess that more general relation will be of this sort. These must be, since it's in matrix mechanics, this must be quantum mechanical mechanical operators, and these are here these are classical dynamical variables constructed out of x and x dot. So these are classical dynamical variables what I actually constructed out of x and x dot. So what I actually mean is these are classical functions. These are not operators in the sense of these ones. So, and these functions, those are the full set of classical dynamical variables in classical mechanics are given by the functions constructed from x and x dot. So those kind of objects will sit here, okay? And so we need to understand this relation. We understand this relation so far, but we need to understand this more general type of relations. Now, a concept which is useful in asking this kind of question is cutting open and sewing of path integral. So let me discuss that. Cutting open and sewing of path integral. So you start with the path integral dx I to f e to the power I h bar s I f of x, which is given by f I. Now what you could do is to insert a completeness operator at some time t. It is pictorially, it would look like the following. So this is t, this is x, and you have the initial point and the final point, and then there are paths. This is the integral over you are calculating. So this is ti and this is tf. But choose an intermediate time now at t and cut the path integral open at this. So this is the entire set of states at this level t. Okay, so that is the identity operator that you are inserting, and therefore you would be writing integral dx f x comma t x comma t I. Okay, so what it means that so the first part is I to x comma t. So at this particular time, you are going to all sorts of x's at that time and getting the result, the matrix element, and then from each of those points, you get the propagator again running from time t to time tf, and then finally you are integrating over all those points. So that is like cutting open and then sieving. So if you write this factor, if you write this result in terms of path integral, it will look like integral dx. This is the ordinary integral. Then integral dx from I to I to star, okay, e to the power I by h bar is I star x, and then integral dx from star to f e to the I by h bar s star to f x, where star represent t comma x. Okay, so this is where you are cutting the path integral open, and this is how you are sieving it back. Okay, so I mean, people use this language. You cut open the path integral here, put some insertion there, and then sieve it back. So that is what we're going to do right now. We're going to do now. So for example, a simplest insertion is a simplest insertion is x of t, which means you are inserting an x dynamical variable at time t. So then the quantity that you are trying to calculate is I to f e to the power I by h bar is I to f of x of t. Now, in order to interpret this in the matrix mechanics language, okay, this is just a calculation that you can perform once you know how to do the path integral. You can perform it in principle, but what is the analogous expression in terms of the matrix mechanics? So you cut open the path integral at x comma t, at t. You cut open the path integral at t and sieve it back. So that would be integral dx f x comma t, then x comma t I. And then this x is a c number because we have written the same thing, except that we have cut open the path integral in this form, and then each factor we have written it back in terms of the matrix elements. Yeah, so x is sitting here in this case, so that is this x. Now this x can go into this, can pass through this state. So this is integral dx f x vector x operator at t, x comma t, x comma t, I, right? And then after sieving it back, it means that you replace this thing by identity. So you will just get rid of it. So this is f x hat. So that is the correspondence. If you in the path integral, if you insert a classical function xt, then what you are basically calculating is the matrix element of x operator at t, Heisenberg operator at t, between these initial and final states. Okay. Now, this is the simplest case, but things a little bit more complicated when we take multiple operators. So let us try to ask that question.